next speaker is one of the academics, Gennady Mishuris in Wales. Okay, so he will be talking about an effective criterion for a stable factorization as equals in the 2 by 2 using the algorithm of the package which Natalia was talking about.
Okay. Dear colleagues, thank to everyone who survived to the last talk. So it's a really difficult was because this was very intensive workshop. So actually you understood that what I did. I thought that I will have half an hour presentation, but in fact I have two of those because it's actually accumulated. So you're already ready to listen what I'm going to deliver. So this is the same set of authors, and the title is here, and I think this is answer to Christina's question, because she also mentioned that, when we start doing factorization, we do not know whether canonical is existing or not. We are doing many different stages to try to identify this, and then we finally come to the circle. But the same question actually came in the previous workshops when even the statement or conjecture was made that all physical problems of classical physics, if the researcher has experienced enough, finally receive proper Wiener-Hopf, probably partial indices would be zero, so everything would be canonical. But it was a conjecture, and this conjecture contained very important part that the researcher is wise, experienced, and could do the job. So if you do not have this important statement, that even the conjecture immediately is wrong. So this is absolutely clear. So on the other hand, we want to answer this question effectively. So the very important point here, this statement effectively. So actually, the part of the European project, actually, quite a few of us here are members of this consortium, and the first paper is exactly what now just reported by Natalia. So having this package ready, so we want to sell this, of course, for free, but we want that people use it. Unfortunately, in MAP also this is already mentioned the problem, so we will try to overcome this. So one of the application was done simply to show that it's not only the toy, what you can play 2 by 2, 3 by 3, 5 by 5, 6 by 6, or 25 by 25, one specific matrix. You really can use it in a real scientific computation. So one of the application already was published, and I'm not going to speak about this as application in nonlinear Schrödinger discrete equation. And I'm going to speak about the last one. It just will appear, it's already on archive, and just will appear in Royal Society. So let's start. So we have matrix A, and we would like to factorize this, and we hope that it's stable, so it's canonical, so then we can factorize somehow. I'm not speaking now about any polynomial one. It's very complicated matrix. I want to do something about this. I have no idea. So what I should do, so the desirable strategy would be, I know that it's definitely partial indices are zero, so then I can approximate this reasonably. So then I go to the to estimate what is, okay, it's another challenge, how to estimate the stability region. Then we're doing any appropriate approximation. What I mean appropriate, we have several options. Actually, yesterday we have very good descriptions of some of possible options. Pole removal, I don't want iterative, polynomial, this, okay, what type of approximation you want to use. And of course, appropriate means that you would later would be able to restore the factorization from this appropriate approximation. It's not simply approximate, but you can factorize your factorization. Okay, so what we know about this, so knowledge, zero knowledge usually, if it's not specific structure, it's not specific space, it's really, or we can only rely on that conjecture I just mentioned. Estimation of the stability region for arbitrary matrices is also a hassle. So, but this is a bit easy because this is a lot of things are available, so we can do something, and then by doing this, we remember that we are doing this in specific space, then we can finally factorize this. So So we have, you see, there's two groups of the pieces of the steps on this strategies. So then some of them are independent of us, or very hard, so they are in red, but something what is really good, so we can rely on that. So what we are proposing something different. So we tell you, okay, let's assume that the matrices are stable. It's very complicated, but it's stable. So if it's stable, we hope that we will try some appropriate factorization. We will do this. We will do this exactly as Natalia mentioned. So this means that even if the partial indices of that approximation would be unstable, we would see it. And then we will try, since again the approximation is good, so for some reason we will be able to evaluate the stability region for that approximation, not for the matrix, but for the approximation. So look, here we're speaking about stability region of the original matrix. Here we're speaking about stability region of the approximation. So as only the original would fit in these new areas, then we are fine, and we can say that the original was also good enough. Then you can continue your approximation to the end, whatever accuracy you wish you would have. Okay, so now it's good that practically everything is ready. The sign showed us that we should really do some additional theoretical job, but then if you've done this, we will be okay. The same can be told about left approximate factorization, so I'm not going to speak anything about this because we already know that the package would create simultaneously both of them. But if you do not have that option, you can always transform your original, then do everything on the right and transform this back. It's not a big deal. Okay, so what is expected result from that type of strategy, what was suggested? So the idea was that, okay, we started with approximation, we have immediately stable. So stable, we have the stability region. Then we are continuing this, and finally we catch the original matrix is the end of the story. It's only matter how accurate you would like to have your approximation. That's it. Then, good news, perfect, so we can draw. So then we are going to the next possibility. We started with something and it's unstable. Since unstable makes no sense to even search for any radius, but we try, okay, maybe if you come closer, with everything would be stable. We did this, we are stable. We again come to the original situation. We are very happy again, everything is stable, very good. But what happened if so the answer is yes, partial indices is stable, and we simultaneously have approximate factorization. You can have any accuracy of that approximation. You are done, everything is perfect. So then we do the same story. We start with a stable. We're continuing, we're coming with approximation closer, but apparently the radius of the approximate decrease in stability decrease, and you never reach your original matrix. So this means that your matrix A is not really canonical stable factorizable, so it's a bad story. So then, unfortunately, then you cannot simply come inside the stability domain. And you can do another. You can believe that maybe another strategy. You are coming closer with your approximation, and you're always on an unstable path, and then you again have the same conclusion that there is no stable, so the matrix was not have partial indices which are not stable. So we know the answer, but what is interesting here actually that this case in a sense is better than this, because this case provides you additional information, because when you're moving with approximation path closer to the matrix A, if your unstable partial indices are the same, it gives you probably information that your original matrix maybe also is the same, and you are on a proper path to reach your unstable matrix. So this is actually create a hope for me and for everyone that we can be successful in approximate, even unstable cases. Okay, so how to realize this? So we do approximate matrix polynomial, approximate with a matrix polynomial. Natalia did all the preparatory job. I'm not going to speak about anything. We are searching exact factorization. So these two conditions should be preserved. So we have the hammer. We have the tool how to work with this. So then the problem is that if I'm doing this, what might happen that at any of the stages, even we are, for example, having all the coefficients rational, it might happen that at each of the approximation stage, the determinant may be factorizable, not factorizable, factorizable, not factorizable. So we want to avoid such case. So we want to be with coefficients, with the rational coefficients, but simultaneously not to have this bad interruptions on the way. So what we can do, we need to create the nail, that this nail would guarantee that everything would be okay to the end. So this is the story. We are simply not considered absolutely arbitrary matrix A. It will be a 2 by 2 matrix and strictly non-singular. I would in a moment will explain what does it mean. And we will, our task is factorize approximately this a 2 by 2 matrix, strictly non-singular, and to create the stability region for that approximation. And inside, so actually this bit, what I'm telling here, it's not in the package. So the package is on the top. So the hammer is different. So this is something what, okay, this is another story we'll discuss. So okay, now I'm ready to really tell you something. So we have the matrix 2 by 2. This is, we are speaking only now about right factorization. We should find this factorization like this. We have no idea what to do. So what we do know, we can probably extract some information from the fact that this is strictly non-singular. So this means that the two A11 and the determinant two binders, they are factorizable, and we will use this information extensively. This is simply to be more convenient. We wrote that the first is kappa and the other is theta plus 2 kappa. It could be kappa 1, kappa 2, but we will actually leave this kappa 1, kappa 2 for the real partial indices, and this is something for auxiliary. Okay, so we have some information. We would like to use this, and exactly to use this in a way to create the nail which eliminate the problem with the exact factorization of the determinant. Okay, so so this nail. So what we are going to do, we will present. We're doing something like a precondition, what is always possible. So we are doing this precondition. We know all those functions. This could be done. So we have m minus b m plus. So if you do something with the matrix B, so the matrix B, why this matrix B is good? Because actually the determinant of this matrix is always factorizable. T in the degree theta, so it's trivial. It's 1, 1, 2 left and right factors. It's only T in the. Okay, it's absolutely trivial. But what we will do a bit even further. So since simply to use that type of splitting, additive splitting is also not a big deal. We can do this, and then we will try to simplify this representation even further, to have it in that form that actually, if you look now in this matrix A, this matrix is plus function already, this matrix is minus function already, determinant is the same as we discussed, it's 1, so we really eliminated a lot of coefficients in this system. So we have really having now something what is very, very nice. So this is our nail. So this nail will, so we are now only working with the matrix A. So this is already done analytically, this is already done analytically, no problem with whatsoever to do those steps. Okay, so let's do this. So first of all, if you look at the matrix A, what we need to create right factorization. But it's funny story, just preparing the talk, I just realized that left factorization is trivial. So if you want to play with this, you would have such another factorization like this, what is completely useless, but it's very nice. So this is something like, okay, nice story, but you cannot use it. So this is not really useful. But then what we are going to do, we will simply, so this is plus function, minus function with the respective Laurent polynomials with the positive and negative degree, so we would simply cut, we would truncate them, and we work on this, would be, all the property would be preserved. So we will work on this, and we'll try to do something about this. So as I just mentioned, so we'll have another factorization, and then we would like to say that this factorization, actually, this one delivers the factorization for the original one with any good accuracy as we only wish. Not simply we are speaking about approximation of the original matrix. We're speaking about approximation of the factorization as well. So this is what I asked to Nigel on his talk. So, okay, so good news. We are very happy. So let's do this. It's just I remind you the possibilities what we have on what we could have on the way. So in the first case we would have everything okay, so we can move, but finally we cannot come to the end in the case B, but can come to the end in the case A. And exactly, so the case 2 is also have 2 subsets, so then we see what is going on. So, but to do all the stuff, we actually miss very important point. We don't have, so if you want to say about accuracy of the factorization, we should have the uniqueness, because otherwise what we are speaking about, if you don't have uniqueness, actually, Natalia forgot to mention that the software what was created has, you know, the GPT, all this learning stuff, they could have hallucination. So this is also the type of hallucination. If you do the same computation for one day for another day, you would have 2 different factorizations with the same partial indices. They're both factorization, but somehow the computer doesn't want to represent the same one. I don't know why. It's a miracle, but it's so we need to do something about uniqueness, and then we can speak about convergence. Otherwise, it's nothing to discuss. So, Natalia with Victor did preparatory job for that. So there was invented the proper normalization for the factorization that guarantees the uniqueness. And depending on what case you have, it's the generalized canonical, what I mean, but the partial indices are the same, or it's not the same. So we have different type of the normalization should be exploited. So if it's P by P matrix, you have so far the results only considering the stable factorization only when all the partial indices are distant. So otherwise, some work should be done, because it's not only it's really the effective stuff. So it's not only statement that you should do this and this, but it's also the algorithm is involved how to normalize the result to have this normalization. Okay, so we are calling this P normalized factorization. So we are now very good in the sense that we are prepared to have unique results, so we can really discuss about convergence result. So let's do the job. We use it would be post-processing what I mentioned about P normalization, because the package doesn't have it. So then we do the job. We factorized everything. We are very happy. And to have some estimation for the factors, we need to say we would like to have something what would be really upper and low bound estimate for this result. Please, this we do not know. We have no idea about this the value, because we don't have exact factorization. So we should know this somehow theoretically, or we can treat this numerically during the computation. Okay, so the good news that the lower bound is very easy to have, but the upper bound is difficult, unfortunately, because it's the Wiener-Hopf algebra, and that it's actually practically the worst norm what you can only think of. And also, actually, we have also hidden error what nobody speaks. Natalia didn't speak. I'm not going to speak, because we are telling, okay, our original coefficients are rational from the very beginning, but they may be not rational, as Ian mentioned. So we would need to do another approximation to have a rational coefficient. So, and I'm not going to speak about that type of error. It's another story. It's also treatable, but I'm not speaking about this in this presentation. So, so what we want to explain, to exploit, we want to assume a bit the more information, we assume that not only given on a unit circle, but a bit more analyticity of the alpha plus and b minus unknown, then we can really do analytical results for the estimate using the Cauchy inequality. I'm not going to because time is short, so I'm trying to run. And this is all, actually everything what I'm speaking is trivial information. It not need really extensive thinking to understand what is going on. So then this is actually you would see it later. The formula is really upper estimation is really crude. Time to time it gives you few orders of upper bound, but it doesn't matter if you do not need this. You cannot use it. Okay, so we are practically ready. So we want to know now. I would like really to know something about the estimate for the factors, what I would have. And that really need a piece of theory, what I'm not going to discuss really, because I do not have time indeed. But please simply observe that we have some specific auxiliary parameter Qn. Actually, Natalia mentioned about this parameter should be less than 1. And what is in it, it's actually the norm between the original matrix A and matrix, okay, and A and so this is the guy. So if you do not have this approximation, simply put here this norm. But then it's two very interesting pieces here. So two coefficients which comes for free from the factorization. And this numerical result will be immediately given to you. And this you probably remember that this when I'm searching for the stability radius of the approximant, clearly the stability radius of approximant would depend on approximant. So would be so in this case would depend on n. It's not the original matrix. We're speaking only about approximation. Okay, so this is two guys as I just mentioned. So the first result tells us something. So this is result about the stability effective. So it's necessary and sufficient actually condition for preservation of the stable partial indices. So if okay, should I read or would be very, because I'm trying to be on time. Sorry, I'm running very fast. So if we assume that the original A matrix A admits the stable P normalized factorization, and then if there is a natural number n such that for any n and for all admissible pairs you remember two pairs coming actually from the estimation of the approximation accuracy, then if the following two conditions immediately fulfilled. So first that an admits the stable factorization, and second that this parameter s is less than 1. And then it's not exactly inverse. The theorem is not exactly in another direction because it's actually much softer. So if conditions 1, 2 is preserved at least for one and for one admissible part, then immediately the original matrix T admits P stable factorization of that kind. And then actually what we can see here, if you think about this is exactly the radius, the stability radius of approximate matrix which we use for the factorization. Okay, so we are actually very close to the end. Partial indices stable, we know what to do. If partial indices are not stable, okay, we are telling, okay, it's difficult, we can do nothing, but I hope I will be able to say something, probably not. So the only, what we can do now, how to estimate the real, the approximants, the quality of the factorization, not the approximation, but the factorization. We have the theorem here. I do not want to concentrate on the formula. So we have a theoretical result. It can be used. And then we have everything. So let's try some experiments. Function is quite nasty. It's not polynomial. It's square roots and here and there. So the only what we wanted that will be analytic in the respective domains. So then we see that there are Laurent polynomials for those matrices. We have immediately the upper bound for this delta n, we're taking psi1 and psi2 simply. Okay, this is additional parameters what can be used depending on whether you converging on this a bit wider domain or not. And then for this particular case, you see how it behaves. It's actually decreased fast enough. And then for the low estimate, we have immediately something like this. We can take one very big number of n0. We can do all the approximation, and then we try to run each consequent approximation. Simply consider this as a low bound, and the upper bound we have exactly what we just mentioned. Okay, so then, okay, don't have time to comment. So this is the case. We started this the first example. The theta was equal to 0, so something what we said. And after computation, what happened that all the partial indices are 0. So it should not definitely be happening. So what might happen? So it will be +1, -1, +2, -2. I mean something like this. So it's only the total indices index should be 0. But apparently for this particular factorization, it's always run with 0. So it was canonical. So all the approximant admit canonical factorization. On this left graph, you see the two low bound, depending what n0 we take in 30 n equal to 30 and n equal to 40. You see they are completely coincide on the range what we are speaking about. So this means that we are really very close to the original solution. You see here the accuracy range. The line here is the upper bound. So then there is some really distance between those two. And then if you look at the of the factorization, you would see that our upper bound is much higher than the low bound what we can numerically compute. So this means that our estimate is really crude enough. Okay, and theoretically we can believe in the result that really everything is 100% sure that our original matrix has partial indices 0, 0 only in this region, more when n greater than 10. Okay, the other example, it's a bit more difficult in the sense that it's another function. I don't want to concentrate on this in the details, so it's some different styles. So apparently during the computation we again have 3, 3, 3, 3, 3, 3, so the total indices is 6. So what we see here that actually for the left factor and for the right factor, we have in this particular case different convergence, but the convergence is fast enough, so it's not a problem whatsoever. And this is a stable case, no problem, even the total index is not 0. And now actually the difference between the upper and low, it's huge actually. It's something like order of 10 and the order of 10. But it only shows that this our formula, what we derived here, it's too crude to be sure to rely on them to be very close. Also, you should remember that we have here something like parameter zeta 1 and zeta 2. You can play with those two. You can do really your upper bound load or not. So it's a lot of play here. Not even what Natalia mentioned, but even here you can have some additional play. And the last one, so the last one is even worse. So then you see what is going on here. It's more or less not exactly what Natalia showed, but of the same style. So no way to even to expect that someone can do the factorization whatsoever, but it's works. So that everything is working. So the good news is that the system really the all approximate solution allows for stable factorization. Even the total indices is -7. But it's everything stable because the difference is exactly 1. Okay, so then, what the takeaway information? So having this, we have the precondition of the original matrix A to something what is better, much better than we do approximation of this. We can evaluate the stability radius here. And actually it's my own view, it's not a view of the full quarter, because in the quarters we have realist, we have optimist, it's me in that case, pessimist is Victor, and we have opportunist is intermediate quarter, who is never taking any side. So I believe that we have much more from that. So I think if you are going in this direction, always preserving the partial indices, we're really even delivering the unstable. Okay, sorry, may I have another, because it's something related to Lasha's talk. So Lasha delivered another approximation for more or less the same. Okay, it was left, but it doesn't matter. So here it's really something what is very crucial, I believe, because Lasha used the so-called natural choice of the partial indices during his approximation step. We are not doing any choice, so our approximations are exact in terms of partial indices, and inside both of us can do factorization exact. So we first of all hope that the same both packages could be done in P by P, and actually I believe from what I just mentioned, actually we can even invent the notion of natural regularization of the matrix with unstable set of partial indices. What do I mean? Someone come to you with a matrix, they factorize this, and a partly matrix is not with a stable partial indices. But the data comes from here, from somewhere. So if your data was colluded, then you are not asked for really factorize what you need to factorize, but something what is in between of reality and someone measured something. So then you can really, using this notion of natural choice of partial indices, you can invent something not equivalent, but something like Tikhonov factorization for the real data, if you assume that the factor should be really not big enough. Okay, I believe it's enough for you to listen to me, because I'm already out for 5 minutes. Yes. Thank you very much again for coming. Yes, please.
So have you seen this case when you're approaching something and the radius is shrinking?
No, we still, actually this is the another conjecture what I didn't time to discuss, and simply I believe that our matrix A is more probably always sitting on a bundle. We discussed this with Lasha already, but I don't have any proof for that.
Yes. So do I understand correctly that you to handle exponents or trigonometric functions, you replace them by polynomials?
No, I simply I'm looking at them as a function on the unit sphere.
No.
It's Laurent polynomials, and I truncated the polynomials.
No, this is what I'm saying. Yeah,
Okay.
yes, so you,
Of course, yes, I'm simply truncating
and
it.
then the idea is that somehow your partial indexes do not depend on the size of truncate.
If those conditions are satisfied. Yes,
okay.
yes.
That's what.
Yes. So in a sense, if this happened, then we're sure we give you the guarantee.
Can I help to make some connection to integrable system? Actually, it is partially answer on your question you asked me already. So if you have what Grigory considered kind of, the piecewise constant matrices, they are related to the full sense system, to maybe more general system, and so those are in their turn related to the Pinlevy equations as isomonodromy preservation, as isomonodromy deformation equations. And so usually, of course, generically with respect to, and if I consider how everything depends on the parameter of the isomonodromy deformation, so parameter on which Pinlevy functions depend. And so usually, of course, we have zero indices, but we have exactly the, okay, so there is no canonical transformation exactly at the points when the corresponding isomonodromy deformation equation has poles.
Okay, so you have
solution has poles.
some different conditions which in a sense deliver the same result. Yes. Actually, Alexander, I believe that next time you would give us some formula how to compute for partial indices.
No, this is, but again, there is in some our example more simple. It is not the formula, just because for again the index is always 1, and say in the 2 by 2 case related to Pinlevy 2 equation.
Okay.
Index always 1, but the question is when it appears when it is not. So it appears at the poles of corresponding solution of the Debye equation.
Actually, I forgot to mention, because I tried to run very fast, that in quantum physics, quantum mechanics, there's really a very important issue of this partial indices, their stability. So this is really, so when I started, I thought that in the classic mechanics, classic physics, we have this conjecture, but in non-classic physics, non-classic mechanics, it's not a conjecture, it's really false. So the partial indices can be not zero.
On that point, I suggest we stop, finish with this discussion, and let us thank you
To all organizers and to all participants who survived to the end talk. I'm very sorry for being late, and we have some last communication to the participants. So please, if you as a result of this workshop would publish a paper, please do not forget to acknowledge to the program. We will send you later a mail with the exact wording how it should be done, which grant we should, not our grants, this grant of the in the Newton Institute should be acknowledged. And also, actually, Natalia forgot to show a very important issue. She prepared something like, if you want to take the code, she had to show this nice, this, you put your phone, you take the picture, and you immediately come to the respective web page. But since she also, my bad school, she was late half a minute, so she didn't do this. So then she probably would do this now. Then everyone who wants, actually, this is free in the sense that you should have map. So this is unfortunate, but it's. Since it was simply like the software were already in place and it cost us nothing, so this. Yes, and the second, even I don't know which is more important, because not everyone would probably publish a paper, but what every one of us should do just immediately after this workshop, we all received the email from the main organizers that please fill the questionnaire. Please do this and write the best words what you can for the Newton Institute and for the funder to be very happy of us and them giving us funding to be here. Thank you very much again to all of you who first agreed to come, who delivered very, very interesting and rich in the topics talk, being on different events, discussing between the line and between the people, and also effectively spending this time, hopefully yes, please.
One bottle to finish from Italy. Okay.
Okay. So one bottle to finish. Everyone should have its own glass, not glass. How to say this? Small. Sure. Yes.
Shot.
No. This is a big one. It's not for.
Oh, that's too big.
Right, shall we thank
Okay.
all the organizers?